So as Chris said, today we're here to present our respective developments on the industrialization of a dry film process for automotive manufacturing. For those of you that sat through the last presentation, PPG and Ford, one of the top questions was, what is the pathway to automate the film application process? From the process and equipment side, hopefully I can present some of the answers in terms of our view and the path forward. So we'll start with an introduction of our respective companies. From there, we'll go into the background of why we have targeted this process and the process that we are proposing. After this, we'll show the data from our trial results to show that both the material and the production concept are ready for industrialization. And then we'll go through our next steps, both what's in progress now and what's to come. So Taikisha is the second largest global paint finishing manufacturing company in the world by footprint. We're a construction company headquartered in Tokyo, Japan. The Taikisha group is made up of 30 companies globally with just over 5,000 employees. We're guided by our customers' first mission statement with our long-term vision to contribute to a sustainable society through the innovative engineering of energy, air, and water.
Next, let me introduce Nippon Automotive Coating, Nippon Paint Automotive Coating. We called NPAC, a key subsidiary of the Nippon Paint Group. NPAC is one of the world's leading automotive coating companies and operates in 22 countries around the world under a strong global network. In response to recent environmental issues, we are developing environmentally friendly paints and coating films with a view to eliminating the need for painting. Today, we are pleased to present results of a collaborative effort between these two companies, showcasing the synergy achieved through this partnership. Next, let's move on to our target. A major theme in the world today, and of course, specifically in the automotive industry, is carbon neutrality. Nearly every major OEM has announced their goal towards carbon neutrality, not only within the use of their products, but the complete life cycle of those products, including its manufacturing. We are all, of course, aware of the paint shop status as one of the primary energy consumers and carbon emitters within the manufacturing portion of the product life cycle. And innovation is necessary in order to achieve these fast approaching targets. So, what can we do as material supplier and line builder to support our customers? The focus comes on how can that directly and indirectly impact our customers' emissions. In upstream, I cannot do this. In upstream scope 3, we can consider reducing material usage, recycling materials, and lowering energy consumption in our own manufacturing process. In scopes 1 and 2, we can provide them with processes with lower energy requirements and a smaller footprint. And in the downstream scope 3, can our processes enable greater product efficiency through weight reduction and be compatible with the EV manufacturing process in general? Instead of simply pushing current methods to their limits, our approach is to offer a completely new option by transforming the coating process itself. How do we achieve this solution? We believe collaboration among the three sectors of the manufacturing industry, the material suppliers, equipment suppliers like ourselves, and OEMs. It's critical to driving sustainable innovation as this conference is focusing on. Today, we'd like to introduce our film decoration technology, share demo trial results, and explore how teamwork can lead further process improvements, helping us get closer to realizing the broader benefits of this solution. Now I'd like to show our proposal. We are all familiar with the best practice in traditional spray coating to reduce energy consumption. However, there is a limit to how much progress can be made when relying on processes that require significant air manipulation, such as spraying and curing. Our dry film decoration process offers a breakthrough. One, the same coating material can be applied to both exterior metal and plastic interior and exterior parts, simplifying the process. Two, energy usage is reduced because air manipulation and curing requirements are minimized. Three, materials can potentially be recycled. Peelable films from damaged or scrapped parts can be sent back for reuse. Additionally, this method is compatible with a wide variety of substrates, enabling the use of lightweight materials like plastic hoods or CFRP doors without the compatibility issues or curing restrictions seen in the traditional coating. While film application is not necessarily a new process, many questions need to be answered in order for it to be truly considered for adoption to replace traditional processes. What are the environmental benefits? What is the energy saving effect on the process? What are the emissions involved with the film manufacturing process? Is there an environmental impact with the film disposal? Or can the material be recycled? Quality needs to be answered from both the design characteristics and the physical application and durability. Can body colors be matched? What other levels of customization can be achieved? How does the color shift as the film is stretched and applied over complex shapes? How durable and weather resistant is the film? And of course, the process cost. What are the comparisons of equipment cost and processes cost compared to a typical paint process? These are extremely important questions which we have set out to answer in our trials to demonstrate the potential that lies within industrializing an OML coating process for automotive. First of all, I'd like to explain about the decorative film. The film is comprised of 4 basic layers sandwiched between protective films. From top to bottom, the film includes a UV clear coat, a PMMA films as a supporting base materials, backed with a design layer and an adhesive layer underneath. The first step is to coat the UV clear coat on the PMMA film. Productivity is high as a roll of film with a width of 1200 to 1500 millimeters can be coated at the speed of 10 to 20 meters per minute with a drying time of only 1 to 2 minutes. Next, the base layer is applied to form the desired body color, designs, or images, which can be applied using printing or similar technologies. Finally, the adhesive layer is processed. I'll also explain a little bit about the characteristic of films. We are a paint manufacturer. Naturally, we have a confidence in our color design. And we aim for quality that can only be achieved by a film made by a paint manufacturer. One example is our pigment dispersion and alignment technology, which enable us to produce films with a high level of design and also enable light and radio wave transmission while maintaining that design. As you can also see in this page, we can achieve designs suitable for film decoration, including designs comparable to spray coating, matte finish designs, designs with various colors and functions. Next is the clear coat on the topmost surface layer. Its greatest feature is that it can be stretched by several hundreds% and still can be applied to automobile exterior specs. The adhesive layer at the bottom of the layer composition is also unique. Utilizing our unique resin technology, even non-polar materials such as PP can be bonded without problems. As shown on the previous slide, it is possible to stretch the film by several hundred%, and this is very important. Here is a perspective on coverage, but the point is very simple. The more stretchable the film, the less film is needed to cover the same workpiece. This is a very important characteristic as it directly leads to the cost and the environmental benefits.
With paint film as the material selected from the process side, there's a lot of different application methods that we can consider. When we look at the primary needs of the automotive coating industry, such as managing complicated shapes, the ability to potentially remove the coating or peel it, transparency control, and application across a wide variety of base materials, we determined that outmold lamination or OML would be the best candidate for this. We'll have some colleagues now start to pass around some samples of parts that have been film coated using OML for you guys to see. To see these parts and the color match compared to a traditional liquid spray painted part, you guys can visit the Nippon paint table over in the exhibition area during the session breaks and get an up close view of everything. For those not familiar with the process, this video will show an example of how outmold lamination or an OML machine works. This video is going to demonstrate the process on a hood, which is a fairly basic and straightforward shape. First, the part's set in place, the film is drawn across, and the piece is lowered further into the machine where the film is creating basically an upper and lower half within the chamber. The chambers are brought completely under vacuum, while the film is then heated with IR heaters to promote its flexibility. Once the film is brought to its desired temperature, the part is going to be mechanically pushed up into the film, with the lower chamber kept at a vacuum and then air released into the upper section to firmly adhere the film to the hood and maintaining a positive pressure on the exterior to ensure an application without any gaps or bubbles across the entire surface. In this next video, we'll show our concept for industrializing a coating or decoration line for fascia production using OML. When you compare it to a typical fascia paint shop, the dry film line is possible to realize dramatic space saving in terms of the size of the building. The line shown is going to include 4 modules, 2 each for front and rear bumper production, which allows us to achieve a net 1-minute tack time per bumper set produced, or a tack time of 2 minutes per module. The main line has main components of the clean room for decoration, the trimming room, and then auxiliary rooms for the controls, pumps, and other equipment. First, the molded part is going to be robotically loaded onto the jig before then transferring into the clean room. The first station will use a robotic cleaning to prep the surface and just make sure that we have a clean surface before it's transferred into the OML machine for the film application. Once the film's applied, the part's transferred out into the trimming area where we have robots laser trimming along the shape of the bumper, and then robots removing the unnecessary and excess film from the areas that aren't required for the production part. That decorated part can then be checked and then loaded by robot onto its transport, which in this case, we're going to show an AMR to send it off to the assembly line. The jig will be sent back through an overhead conveyor to be cleaned if necessary and returned back to the beginning of the process. Or if you have a parts mix, you can swap out jigs here or swap out jigs that are heavily damaged and need to be replaced. In a kind of a preview of some of the results to come, we're estimating CO2 emission reductions in excess of 50% for the decoration process and 80% reduction in both the building size and the part lead time from start to finish. As I kind of showed at the beginning of the video, the tremendous space-saving results can be achieved using this OML-based process to greatly reduce the size of the building, both from a building volume and a floor area, and that lead time going from 2 hours from start to finish when you're including all of the spray, cure, and checking down to about a 20-minute start-to-finish process to reduce your overall parts and WIP. As we mentioned earlier, really the impetus of this is based on the environmental impact of moving away from a traditional spray process. This table is using the same fascia line with an annual output of about 240,000 car sets per year as the basis of comparison. On the left side, you're going to see the improvements that can be made going from a traditional or old school spray process, moving to a dry booth process, and then a high coating efficiency or high TE process. And while those improvements of about 20% of carbon emissions per unit is good, they really aren't enough to achieve the carbon reduction targets of the industry. With the dry film process eliminating much of that air conditioning, completely eliminating the curing oven at the plant level, we're estimating a comparable OML process will yield a 75% reduction in the plant level Scope 1 and Scope 2 emissions when compared to a traditional paint process, or closer to about 70% if you're using a dry booth and high TE application. And for some, that Scope 1 and 2 benefit is good enough, but of course, those doing their homework need to look at the Scope 3 side when you're considering the film manufacturing and then the film waste. And in this slide, we've done that. We've added that in. In blue, you'll see the Category 1 emissions from the paint or film manufacturing, and then gray is the Category 5 contribution from waste paint or waste film. And you'll see that the emissions from the dry film manufacturing process still plays a significant part of the equation. And even assuming the lowest coverage ratio or the most waste film, we're still seeing a 28% drop in CO2 emissions compared to conventional processes. But the film process is more significantly affected by a high coverage ratio than a traditional spray application is to a high TE application. As Iwakoshi-san mentioned earlier, that coverage ratio really is key in terms of your efficiency of material usage. And when you consider a high coverage ratio, your benefit, even including the Scope 3 emissions of the film manufacturing and waste, is greater than 50%. And yes, the emissions of the production of the paint film, it is relatively high, but that's because you're moving the cure, as has been mentioned by Iwakoshi and in the presentation before us, you're moving that cure from the plant level to the material manufacturing. But since you're only curing the film, you're not having to heat up the entire body in the process. That's where you're more than offsetting that increase with the benefits of the process at the plant level. In terms of the process energy cost, you can imagine these reductions in emissions are directly correlating to a reduction in energy usage and energy cost. Since the dry film process, again, eliminates any use of gas or steam in the process and only uses electricity at a rate which we estimate to still be less than a traditional paint shop. Assuming the unit prices we show here, that leads to an annual cost savings in process energy cost alone of about $900,000 per year, or almost $4 per vehicle set if you want to put it in that production number. And of course, this is before considering the change in material cost of paint film versus liquid paint, but it also doesn't factor in the labor cost savings of a fully automated line. This benefit is good in and of itself, but that overall reduction in consumption is really the main point here. Even as some plants move towards full electrification, electrifying ovens and air houses, this is really only shifting consumption from gas to electricity. And while your direct process emissions may be reduced or eliminated, the emissions caused by that increased consumption and generation of electricity needs to be considered when you're looking at the overall package. So to summarize, we really see an incredible amount of potential in a dry film process for decoration. The line is fully electric, uses less energy overall by eliminating the ovens, large scale and precision air conditioning, and reducing water and waste treatment consumption. These features directly contribute to a significant reduction in CO2 emissions. The process uses a much smaller physical footprint. It can also be fully automated to give consistent quality, and a modular line structure gives you design flexibility and also reduces the time to construct the line compared to a traditional paint shop. And as well, a clean and solvent-free process leads to a much safer and much more comfortable working environment for your production team members. I'll hand back over to Iwakoshi-san to review the trial results from their material application.
Yes. Okay. Next, we will show you the demo trial results. We use NPAC silver metallic film to laminate two types of bumpers. The area circled by the blue dotted line is the decorative area where our method was used. The one on the left is a split type, and the other is an integrated type. As you can see, the film can be applied neatly to the complex three-dimensional shapes. Decorating one-piece bumpers was very challenging, but we overcame this difficulty with Taikisha's new OML molding process and NPAC film. Oops. Oops, sorry. Oh. Okay, so this is a OML. This is a demo trial photo, and from OML film and sorry, from the OMM process to the laser trimming, we can do it. So that we can get the prototype from here, and then yes, okay. Oops. I'll show you the data of the. I'm sorry. The data of the elongation data and the color shift data. As you can see, the Taikisha developed the new OML process, and we can, the elongation rate is less than the 200% stretch. So we can, so the color change is very minimized. As you can see from the 6 areas, we can measure the color change.
Trying to help.
Sorry. And the delta E is very small value, and this can be good. And sorry. Yeah, and then Taikisha develops molding technology and does not cause localized high stretching, and NPAC develops film that can follow the stretching and does not cause hue shift. With our combined expertise, Taikisha and NPAC have realized the film decoration of the integral type of bumper. Okay, so this page shows the repairability. If the damage is very big, yeah, you can transfer to the, oh, sorry, yeah. The entire part might be an option, but for damage like this, it can be repaired in the same way as a conventional repair process. This includes sanding, applying primer and surfacer, water sanding, followed by base coat application and clear coat painting. And final step is polishing. That's it. So for the next step, Joel, explain about that.
So first, I'd like to call back to those verification questions we posed at the beginning, the questions we really need to answer if we're going to seriously consider a process that some could consider transformative or radical, depending on your view. From the environmental considerations, we're projecting a 75% reduction of the CO2 direct process emissions, or 30 to 50% reduction when you're considering scope 3 as well. As Iwakoshi-san developed or demonstrated, excuse me, the color matching to a painted body is absolutely achievable, and progress continues to be made in maintaining that color over high stretched areas. Not only that, but the coating durability is absolutely in line with industry expectations, and the repair process development shows promise to meet that expectation as well. From the process side, we can support parts with geometries ranging from full one-piece bumpers to hoods and sheet metal components, while the stretch rate can be managed through the simulation of the wrapping process and optimization of the molds. And from a cost effectiveness perspective, we project an OML line would lead to a significant reduction in process energy costs, not to mention the overall operating cost reduction coming from an automated process, and of course, some reduction in capital cost as well. With these considerations from the Taikisha perspective, we really believe in the significant potential of this process. So what are we doing to realize this potential? We've taken the steps now to take this from a concept to detailed design and now a fully functional demonstration line at our R&D facility in Zama, Japan. This line is going to function as our living laboratory to develop and improve each element of the process, test out materials from film manufacturers, and test out production parts of OEMs. The line is now running as of this January of this year, and we've started customer trials on the line as of March of this year. One of the key elements of development is in the OML machine itself. This OML machine from Fusei that was shown earlier in the video is really only suitable for batch type production, and the height of the parts to be processed is limited by the machine geometry to kind of a flat, based on the flat fixed nature of the equipment. You can really only do that part. Our new machine at Zama features a flexible concept for setting the film that follows the shape of the part, and the flexible heaters following the contour of the part shape as well. This allows us to process much taller parts, up to 1.1 meters on our demonstration line. Please don't consider this the limit of the process, as we'd be able to design the specific vacuum forming machine around the OEM parts. The machine's also designed to have the ability to have parts convey in and out, enabling series production in an inline process. Also quickly like to highlight the development and process tuning of both the robotic CO2 trimming and the robotic film peeling process. Both of these are ongoing at Zama, and really automating these processes is going to be key to the achievement of a high quality and fully automated production line. This just quickly goes over an overview of the line we've built. It's a full-scale production line. It would be exactly what you would get essentially at a customer facility if you were to enable this into your production. One addition you will see is the added UV curing station, as we found that some material suppliers, I think Iwakoshi mentioned as well, a UV cure required for that clear coat outer layer. But again, it's not a thermal cure. You're not using gas. You're using a lot less energy. And as I've mentioned, the line is in operation, and we'd love to work with you on this process development. That's why we're here today, to get the word out that we want to develop your materials with you. We want to work on your process trials because we really believe in this process and what it could mean for the coatings industry. Basically hearkening back to the theme of today's conference, collaboration drives that innovation. We've got the equipment ready. Nippon and others have presented, have the material side. And from the OEM side, we are seeing interest. We have 5 OEMs on board doing production trials right now, and certainly more to come. From here, we've begun rolling out the introduction of the process through our exhibitions in both Japan and here in the US. We're continuing our conversations to keep that bond of the manufacturing trinity. And the next major step of development that we are actively working on in Japan as well is the ability to vacuum form on the OML machine complex metal parts. So including doors, including hoods, including deck lids that are going to have holes and have hems and be difficult to pull a vacuum on. We have process developments right now in place that we feel will be suitable for those applications. And with that, thank you for your time, and we'll look forward to the questions.
Thank you, Joel and Ayako, for your presentation. In the interest of time, we are probably going to have to move on to the next talk. You do have 27 wonderful questions waiting for you to answer in the app. So you're one behind utilizing satin film vehicle customization. So somebody else enter a question, make it a tie. All right. But thank you again for your talk. It's very interesting, and we will transition to the next speaker.
Thank you.
Thank you.